Hi, my name is Grégory Sonnet, and I'm excited to talk to you about a work we did with Badr, Yubi Idrissi, and Marine Aziza on virtual adversarial active learning. So, over the last few years, there are a lot of progresses on natural language understanding, which have shown new incredible architectures, providing really high performances when tested on large available datasets. Nevertheless, in real-life application of dialogue system, like for call center, labeled data are not always available, and an annotation phase is required to constitute a training dataset or at least for testing existing method. The main problem is the annotation requires experts to understand correctly user intention and slot information, which can be costly or time-consuming. Here in this work, we propose a framework combining semi-supervised learning based on virtual adversarial training and entropy-based active learning on the top of an intention joint NLU model. But this framework is model agnostic. So technically, we adapted the virtual adversarial training for joint NLU. For this, adversarial perturbations are computed over the two NLU losses rather than each individually. Else, the two perturbations can annihilate each other, and it also reduces the training speed. The main advantage of virtual adversarial training is it helps to regularize efficiently the model through local distribution smoothness. It results in better model calibration, prevents the model to overfit, and making the entropy-based samplings more efficient. For active learning, our confidence score is performed according to the highest entropy of the utterances, combining intent confidence and slot confidence. For intent, we are using directly the entropy, and for slot filling, we are averaging the entropy of each word in the utterance or the sentence. Both scores are then normalized by using the 99th percentile of each score. So this is a view of our method model. So the left part corresponds to the sentence encoder and the right part to the decoders, which contain the intent decoder on the top and a slot decoder at the bottom. Contrary to computer vision, where the adversarial noise is added directly on the image, here the adversarial noise, defined by R, is added at the word embeddings level. So for tested our approach, we test on two well-known datasets, ATIS and SNPs. We simulate the annotation process by unlabeling all the data and keeping only a small part of labeled data. An initial pre-training is performed with this slice part of annotated data, randomly sampled. Then this small label training set is doubled by simulating the human annotation by sampling data according to the entropy. And the final training is performed with this dataset. So let's now talk about the results. So we conduct experiments on very low amount of annotated data, starting from only 10% of the ATIS corpus and 2% of the SNPs corpus, which correspond to approximately 400 and 300 labeled data. We compare our method against random samplings, which is a strong baseline for active learning, and also without virtual adversarial training. Results show that our method in orange are able to provide gains over random samplings and entropy samplings without active virtual adversarial training. So, and also the largest gains are obtained in the very low data regimes. So this framework makes it easy to integrate for production, as it makes the training more robust and samplings much more efficient. And this without adding any additional or expensive method to be able to sampling the data to be annotated. If you want more detail, our paper is available on arXiv, and also the code is on GitHub for reproducing the experiment and the results. Thanks for listening.